We spent a lot of time celebrating triumphs, breaking records, showcasing brilliant successes. We love hearing about what went right.
We absolutely do. Success stories are inspiring.
But what if I told you that some of the most profound lessons, the real aha moments that genuinely push us forward, actually come from when things don't go as planned?
Hmm, that's a powerful thought, looking at the other side of the coin.
Exactly. Today, we're diving into precisely that. The critical, often sobering, and profoundly insightful world of understanding why things fail.
And what we're calling failure analysis, it isn't about casting blame or dwelling on setbacks. Not at all.
Right, it's not about pointing fingers.
Instead, it's about acting as meticulous detectives, sifting through every piece of evidence when a project deviates from its course. Maybe a design proves flawed.
Or a material doesn't perform like you expected.
Exactly. Or a structure simply falls short of its intended purpose. It's a rigorous, methodical process.
So dissecting what went wrong.
Yes, dissecting it, not just to understand the event itself, but to extract invaluable knowledge. This knowledge ensures we build smarter, safer, and more reliably in the future.
Fundamentally transforming adversity into an engine for progress.
That's the goal.
So get ready, because we're taking a deep dive into how engineers, architects, project managers, how they transform their toughest challenges, their deepest disappointments into blueprints for improvement.
It's a fascinating field.
You'll discover how every setback, from the smallest deviation really to the most dramatic collapse, can be meticulously investigated and analyzed, ultimately shaping everything from the resilience of the buildings around us to the very way we approach complex endeavors.
A continuous cycle.
We'll explore this fascinating detective work, the hard-won lessons learned, and that continuous cycle of improvement that makes our built world progressively more robust and trustworthy. Hashtag defining failure beyond catastrophe. When we hear the word failure, our minds often conjure up dramatic, catastrophic images, don't they?
Oh, definitely. Headlines grab you. Bridge collapses. Buildings toppling.
Right, those spectacular structural mishaps. But our sources reveal a much broader and, frankly, more nuanced definition, especially in the context of projects, systems, and engineering.
That's right. It's not just about things falling down.
It isn't, is it?
Absolutely not. And that's a crucial distinction. What's truly fascinating here is that a failure can simply be a deviation from a target outcome.
A deviation, okay.
The PMBOK guide, for instance, makes it very clear that a project rarely performs exactly as initially planned. It's almost unheard of.
Right, too many variables.
Exactly. It highlights that projects are inherently influenced by a complex system of interactions, this dynamic web involving internal factors like team dynamics,
Yes.
external factors such as market shifts or regulatory changes, new requirements popping up mid-project,
Happens all the time.
and the ever-present influence of various stakeholders. All these elements exist in a delicate balance.
And they can cause things to go off track.
Precisely. They can cause components, or even the entire project, to fail or fall short of expectations. So it's a far more pervasive concept than just a headline-grabbing disaster.
That reframes it entirely. When you consider that broader definition, it becomes incredibly relatable, doesn't it?
Very much so.
I mean, think about your own projects, whether at work or a personal endeavor, or even just planning a family event.
Yeah?
How often do things go exactly to plan without a single hitch or unexpected curveball?
Probably never, right? Life happens.
Exactly. This expanded understanding moves failure from a distant, dramatic event to the everyday reality of any complex undertaking.
Precisely. So if things don't go according to the initial plan, that constitutes a failure in this operational context.
Okay.
The PMBOK guide provides excellent practical examples. Imagine an infrastructure project, let's say a new highway. During its execution, a court decision suddenly mandates a significant change to the original designs. Maybe it requires a different route or redesign of certain structures due to environmental concerns that weren't fully accounted for initially.
Okay, so the original plan has to change.
By necessity, the original plan has failed. It's no longer viable. Or consider a technology project. A sophisticated computerized model works flawlessly in a controlled lab environment, shows all components integrating perfectly, looks great,
Sounds promising.
but then in its real-world application, the technology inexplicably fails to perform as predicted. Maybe due to unforeseen environmental variables or user interactions the model didn't capture.
So the lab success didn't translate.
Right. In both these scenarios, the project team isn't dealing with a physical collapse, but they're compelled to regroup, rethink and replan.
They have to adapt.
They have to. And this raises an important question for project management. Isn't inflexibility itself a form of failure?
That's interesting. Explain that.
Well, the inability to adapt, to pivot intelligently when new information or circumstances emerge, couldn't that be seen as a significant project failure in terms of its ultimate value generation and successful completion?
That's a powerful point about inflexibility. It suggests that rigidity in planning, even with the best intentions, can be a major flaw.
It can be.
And the PMBOK guide really backs this up, doesn't it? It explicitly states that the idea that projects should hold firm to plans and commitments made during the early stages, even after new or unforeseen factors emerge, is not beneficial to stakeholders.
Exactly. It's right there in the guide.
So blindly clinging to an outdated blueprint, refusing to acknowledge new realities, it's not just inefficient, it's actively counterproductive.
It can significantly limit the project's potential for generating value.
It effectively becomes a failure of foresight and adaptability, even if the original plan was meticulously crafted.
Precisely. And then if we shift perspective a bit, look at lean construction, as presented in the Practitioner's Guide to Essential Lean Research.
Okay, what's their take?
They offer an even more direct and comprehensive definition. They categorize breakdowns as deviation from target outcomes.
Breakdowns, okay, similar idea.
Yes, but this broad category immediately encompasses plan failures, errors and defects, and occupational illnesses and injuries.
Oh, wow. So it includes safety incidents, too.
Yes. This definition instantly expands our understanding beyond just design or material issues to include the critical human element.
So whether it's an error in a calculation, a defect in workmanship,
or sadly, even a workplace injury, each represents a deviation from a desired, safe, and efficient outcome.
that's a very comprehensive view of breakdowns. It truly highlights that human error, design flaws, material imperfections, even safety issues are all part of these deviations from the ideal that we're talking about.
It brings it down to the ground level.
It moves the conversation beyond abstract theory and directly into the daily realities and inherent imperfections of any complex undertaking, especially in fields like construction.
And it's important to clarify that adaptation isn't just about chaotic, uncontrolled reactions. You can't just wing it.
Right. There needs to be a process.
The PMBOK guide stresses that adapting should always be done with a holistic view, employing a proper change control process.
To avoid unintended negative consequences.
Exactly. Things like scope creep. For those unfamiliar, scope creep is when a project's objectives or deliverables start to expand uncontrollably beyond what was initially agreed upon.
Which often leads to budget overruns and timeline delays, right?
Almost inevitably. So to effectively manage this, the PMBOK guide outlines crucial capabilities supporting adaptability and resilience.
Like what?
Things like diligent planning, responsive project work, reliable delivery, consistent measurement, and proactive management of uncertainty.
Okay, a whole suite of capability.
What's vital to grasp is that these performance domains are not isolated, siloed efforts. They operate as an integrated, interdependent system.
Interdependent, meaning they all affect each other.
Yes, they run concurrently throughout the project lifecycle. So truly effective adaptation means all these elements work together.
Like the finely tuned systems of a living organism, maybe, constantly sensing and adjusting.
That's a powerful way to put it. Yes, like an organism maintaining its internal balance.
So it's not merely about reacting to a problem once it arises.
Oh, it's about having robust, integrated systems in place beforehand to manage that reaction effectively and prevent new issues from spiraling out of control.
And the idea that these domains run concurrently and are interdependent is key.
Absolutely.
Planning isn't just a phase you finish and forget. It's an ongoing, dynamic process woven into every stage.
Right. This prevents isolated efforts from becoming new vulnerabilities. Instead, it fosters a truly resilient and responsive project environment.
Okay, so if we accept this broader definition of failure as a deviation from a target, then the core of failure analysis truly becomes detective work, doesn't it?
It really does. You're searching for clues.
It's about not just identifying the symptom, but tracing it back to its root cause, the moment or factor where that deviation truly originated.
Finding the source.
And our sources point to various critical stages where things can go wrong. The initial design, the materials chosen, and the construction process itself.
Precisely. The journey from a nascent concept to a finished building or a functional system is, well, it's fraught with potential pitfalls.
A long road.
And our documents meticulously shed light on how each stage contributes to what we ultimately perceive as a failure. underscoring the interconnectedness of the entire process.
Okay, let's break that down. Where do we start? Design.
Let's start with the design phase. In construction management, this phase is meticulously broken down into preliminary and detailed design,
Right.
culminating in the end product of a comprehensive set of plans and specifications.
Blueprints.
Exactly. What's truly fascinating here is the sheer complexity and interdependency inherent in this stage. For example, the architectural layout. What might seem like just an aesthetic or spatial decision.
How the building looks, where the rooms are.
Right. That layout directly impacts the weight support characteristics of the floor structure and, consequently, the ultimate selection of the entire structural system.
Wow, okay. So aesthetics affects structure directly.
Profoundly. All designs, architectural, civil, structural, mechanical, electrical, are profoundly interlinked.
Like a web?
A very complex web. This means a seemingly small, isolated oversight or a change in one discipline's plans can cascade.
Creating massive, unforeseen implications for others.
Absolutely. Potentially leading to significant challenges or outright failures down the line. It's a vivid illustration of how every stroke on a drawing board carries immense responsibility.
That truly highlights the immense responsibility involved in design and the critical need for early and continuous coordination.
Collaboration is key.
So an architect's aesthetic choice isn't just about appearance. It can fundamentally shape the engineering challenges and potential vulnerabilities of its structure.
It really can. This interdependency means a small miscommunication or oversight in one discipline can very quickly snowball into a major problem elsewhere.
Which underscores why communication and multidisciplinary collaboration are paramount from day one.
Absolutely essential.
Yeah.
And this is where modern tools are really revolutionizing how we prevent these design-related failures.
Technology stepping in.
Yes. The BIM handbook discusses the transformative power of parametric modeling in fostering collaboration. BIM stands for Building Information Modeling.
Okay, parametric modeling. How does that help?
Especially for complex designs, like elaborate, doubly curved envelope geometry or intricate truss systems. Imagine in the past.
Look for these tools.
Right. When the architectural model changed even slightly, huge amounts of calculations had to be carried out every time, manually.
Oh, I can imagine. Tedious and error-prone.
Exactly. Prohibitively time-consuming, tedious, and prone to error, as the source says. A guaranteed recipe for design failures.
So what changed?
Well, the custom integration of parametric modeling with structural analysis applications drastically reduced these design analysis feedback cycles.
So the computer does the heavy lifting, recalculating automatically.
Essentially, yes. This isn't just a convenience, it's a fundamental shift. It allows engineers and architects to explore more options, identify clashes early.
Like where pipes might hit beams.
Precisely. And basically perform continuous automated failure analysis at the design stage.
Preventing problems before they're built.
Significantly mitigating human error and improving the overall robustness of the final design.
So these advanced design tools themselves are evolving specifically to prevent these kinds of failures.
They are. By automating incredibly complex calculations and drastically improving coordination between disciplines.
It's a powerful example of technology learning from past vulnerabilities and proactively building a more resilient design process.
Definitely. But design is only one piece. Beyond design, the materials themselves can be a primary source of failure if their properties aren't fully understood or respected.
Okay, so material science comes into play.
Big time. Fundamentals of Building Construction offers a compelling example with wood.
Wood seems simple, but I guess it's not.
It has complex behaviors. It explains that tangential shrinkage is so much greater than radial shrinkage.
Meaning it shrinks differently depending on the direction of the grain.
Exactly. As a log dries, this differential shrinkage creates high internal stresses within the wood.
And that leads to?
Radial cracks called checks. You've probably seen them in old beams.
Ah, okay. Those splits.
Furthermore, the specific position of lumber within the tree, whether it's heartwood or sapwood from the center or outer rings, also significantly affects its seasoning distortions, how it warps or twists as it dries.
So it matters where in the tree the wood came from.
It does. This isn't a defect in the wood itself. It's an inherent natural property.
But failing to account for it leads to failure.
Absolutely. Failing to understand and account for these natural tendencies in design and construction will absolutely lead to performance failures like warped doors that stick or cracked beams.
That's a fascinating insight. It means even a natural material like wood has inherent failure modes.
It does. Modes that engineers and builders must deeply understand and meticulously plan for.
It's not just about picking a strong piece of wood.
No, it's Knowing how that wood behaves over time under different moisture levels and how to mitigate those tendencies in construction to prevent future issues.
Got it. What else about materials?
Well, understanding wood further elaborates on how different wood species vary significantly in their decay resistance or durability.
Some woods resist rot better than others.
Much better. It emphasizes the crucial need to select a naturally durable wood like cedar or redwood or a chemically treated wood whenever moisture content cannot be consistently kept below 20%.
20% moisture, that's the magic number.
It's a critical threshold. If that's breached for extended periods, the wood becomes highly susceptible to fungal decay, leading to structural compromise and eventual failure.
Okay. What about other common materials like concrete?
Concrete has its own vulnerabilities. Fundamentals of residential construction explains that in very hot weather, the chemical hydration reaction that causes concrete to harden is greatly accelerated.
It cures too fast.
Yes, it can lead to a phenomenon called flash setting, where the concrete begins to cure prematurely, sometimes even before it can be properly placed, screeded, and finished.
That sounds bad. What happens then?
This premature hardening can result in weak, cold joints between pores or internal microcracks, preventing the concrete from achieving its full design strength and long-term durability.
So how do builders deal with pouring concrete on a hot day?
Engineers become incredibly precise with cooling strategies. This might involve using cool aggregates, replacing some mixing water with crushed ice.
Crushed ice in the concrete mix? Seriously?
Absolutely. Or even bubbling liquid nitrogen through the mixture at the batch plant just before delivery to cool it down significantly.
Wow, that's extreme.
These aren't just minor adjustments. They are absolutely essential for preventing fundamental material failures that would otherwise compromise the entire structure.
Think about those common occurrences you see. An old wooden door that warps and sticks in its frame, or a concrete slab that develops unsightly and structurally significant cracks.
Yeah, you see it all the time.
Often, the root cause goes back to these fundamental material properties and a failure to properly account for them during the initial design or the construction process.
It's a silent kind of failure, often unseen until it's too late.
But a failure nonetheless that impacts aesthetics, functionality, and safety.
Exactly. But even with flawless designs and perfectly understood materials, the execution on site remains a critical factor. What happens during construction?
The actual building process.
Right. Construction project management drives this home by providing an inspection checklist for masonry.
Masonry, like bricklaying.
Yes, brick and block work. And this checklist runs to an astonishing 31 points.
31. Just for masonry.
Just for masonry. This isn't just a casual glance. It's an incredibly detailed roadmap for preventing failures.
What kind of things are on it?
It covers everything from verifying approved shop drawings and samples to ensuring the correct mortar type is used, reinforcement is spaced properly, grouting is done correctly.
Grouting the gaps inside block walls?
Yes, ensuring it fills completely. And even that, the newly laid masonry is protected from freezing temperatures, which can damage fresh mortar.
Okay, that makes sense.
It specifically emphasizes details like ensuring full head and bed joints, meaning the mortar must completely fill the spaces between bricks or blocks, and providing proper support of high walls during construction so they don't buckle under their own weight before the mortar cures.
Each point sounds like a lesson learned.
Absolutely. Each point on this checklist is a direct lesson learned from past failures, where omissions or shortcuts led to compromised structures.
That's an incredible level of meticulous detail. It really underscores that preventing failures in construction is an ongoing, continuous process.
It is. Not just a one-time check at the end.
Yeah. It's about constant, rigorous vigilance at every single stage of the build, recognizing that every small step contributes to the overall integrity.
Furthermore, Building Construction Illustrated specifies requirements that are direct responses to known failure points in completed structures.
Like what kind of requirements?
For example, foundation wall systems enclosing a habitable space, like a basement, are mandated to resist the penetration of water and soil gases like radon.
To prevent leaks and unhealthy air.
Right. They also have to control heat flow and accommodate necessary openings like windows or pipes, all while maintaining structural integrity. This isn't arbitrary. It's a direct lesson from basement flooding, rolled growth, and radon exposure.
Problems people have actually faced.
Exactly. Similarly, exit corridors within a building are required to be enclosed by walls of fire-resistive construction with self-closing fire doors.
To contain fire and allow people to escape.
Precisely. These are all measures painstakingly codified into modern building practices, specifically designed to prevent common building failures, or, when a hazard like a fire does occur, to dramatically mitigate its impact and allow safe egress.
They are, in essence, practical applications of hard-won knowledge from past tragedies.
That's exactly what they are.
These extensive checklists and exacting specifications are, in essence, codified lessons from countless past mistakes and devastating failures.
They exist to protect you, the building occupant.
By ensuring that every component of a structure is built to resist known hazards, maintain structural integrity, and function safely under stress.
It's a silent guardian, built piece by painstaking piece into our environment.
Okay, so we've covered design, materials, construction practices. What about looking at some bigger challenges? While our sources don't delve into specific, well-known catastrophic events like, say, the Tacoma Narrows Bridge,
No, they don't name those specific ones.
but they do offer fascinating insights into the colossal challenges faced by engineers on monumental projects. These stories of overcoming significant roadblocks are themselves a compelling look at failure in action and how ingenuity can ultimately triumph.
Absolutely. The biography of Isambard Kingdom Brunel is a treasure trove of such stories.
Brunel, the great Victorian engineer.
Yes. Here was a man tasked with projects that pushed the absolute boundaries of engineering at the time, like the Great Western Railway, an unprecedented endeavor.
Built across England.
Right, or designing ships 6 times the size of anything afloat. His career wasn't just a string of successes, it was a relentless series of innovations forged in the crucible of confronting and overcoming unexpected failures.
This is where the human drama behind engineering really comes alive. Brunel's great ship, later renamed the Great Eastern,
A leviathan of a ship.
it was an absolute engineering marvel, a vision of the future. But its very launch, a moment meant for triumph, became a monumental struggle against physics and unforeseen challenges.
It truly tested his resolve and engineering prowess to the limit.
Tell us about that launch. What went wrong? Or maybe what almost went wrong?
Well, the launch of the Great Eastern is a perfect case study in how even the most meticulously planned projects can encounter unforeseen failures. Isambard Kingdom Brunel details how he ingeniously designed the launching ways.
The ramp it slides down into the water.
Exactly. He designed them with limited resilience to ensure an even distribution of the ship's massive 12,000-ton weight. This was a direct contrast to the traditional, absolutely rigid building slip.
Why the resilience? Why let it flex?
His primary concern, a powerful lesson in foresight, was that if the ways settled unevenly, which was likely given the sheer scale and the marshy ground by the Thames, it could distort the flat bottom plates of the ship.
Causing structural damage before it even floated.
Exactly. Irreparable damage.
Yeah.
So the initial launch attempts in November 1857 were indeed fraught with issues.
It didn't just slide smoothly in.
Far from it. The ship moved mere feet, the checking chain snapped under the strain, hydraulic systems failed, and tragically, a worker was killed when struck by equipment.
Oh no, so it was a failure on multiple levels.
A major setback. This forced costly delays and the acquisition of additional, more powerful hydraulic presses. Eventually, he required no less than 18 presses.
18 hydraulic presses.
Yes, 9 at the bow and 9 at the stern, with a combined thrust of 4,500 tons, just to incrementally force the ship down the ways.
How long did that take?
Over a period of 3 months, just inching it forward.
Wow, 3 months to launch it.
This Herculean effort highlights how a meticulously designed plan could still encounter unforeseen ground conditions, mechanical malfunctions, and the sheer unpredictability of large-scale forces, all challenging its execution and pushing the definition of project failure.
So this incredibly anticipated engineering feat faced significant failures, not just in its technical execution, requiring immense force and persistence.
But also on the financial front.
Right. It's a powerful reminder that failure often manifests in multiple dimensions simultaneously. The contractor, Scott Russell, he caused problems.
He did. He actually suspended payments and effectively held the entire project hostage, making what the source describes as cool effrontery demands for payment.
That's a huge deviation from the project plan, a failure of the partnership.
The financial failures were indeed as dramatic and complex as the technical ones. Scott Russell not only suspended payments, but, as the source recounts, was one of those individuals in whose hands money could melt mysteriously away.
Sounds like fraud.
Essentially, yes.
Yeah?
His actions ultimately led to his business being liquidated. Brunel and his colleagues were confronted with the painful fact that they had been severely defrauded.
Could they recoup the losses?
When the company reserved a claim for breach of contract, they discovered Russell had no estate due to prior mortgages, making any legal recourse useless.
Unbelievable.
This truly is a powerful illustration of how engineering challenges, immense financial pressures, and the unpredictable human factor, in this case, outright dishonesty, can intertwine in grand projects.
Pushing the boundaries of what's possible and showcasing how failure can manifest as a complete systems breakdown, not just a broken part.
Exactly, a systemic failure.
Okay, moving from the triumphs and travails of individual structures to the shaping of entire cities, our sources introduce us to Robert Moses.
Moses, a towering, controversial figure.
He's a figure whose monumental projects, while undeniably transformative for New York City, were also marked by significant failures in social, ethical, and political terms.
His ambition reshaped an urban landscape, but often at an immense human and community cost.
How did his methods lead to what we might call failures?
Well, if we truly connect this to the bigger picture, the power broker reveals how Moses systematically leveraged and manipulated public authorities.
These quasi-governmental bodies.
Yes, to circumvent public scrutiny, essentially keeping the public in the dark about his true intentions and actions. This led to fundamental failures in transparency, democratic process, and public engagement.
Can you give an example?
For instance, he ruthlessly removed commercial enterprises, displaced residents, and created expansive green parkland for much of Riverside Park along the Hudson River, a huge undertaking.
Which sounds good on the surface.
But he deliberately allowed existing commercial and industrial structures to remain in the Harlem section of the park between 125th and 145th Streets.
So that section didn't get the park improvements.
No, the result was no Riverside Park at all for a significant 20-block stretch for those communities, predominantly African-American communities. This was a clear and profound failure to serve all communities equitably.
A structural imbalance in urban planning driven by political will or perhaps racial bias.
The source strongly implies racial bias and political calculation were factors. It was a failure of equity.
That's a stark example of how large-scale planning, even while achieving certain grand objectives like building magnificent parkways, can profoundly fail specific communities or ignore critical social needs.
His very decision-making process, driven by a disregard for public input and an almost singular focus on his own vision, could be seen as a systemic failure of civic responsibility.
Creating lasting impacts on urban life and equity that continue to resonate today.
Absolutely. And even his relationships with key political allies like Mayor LaGuardia became strained.
LaGuardia, the famous mayor of New York.
Yes. The mayor became progressively more aware of priorities beyond Moses's singular focus on parks and parkways. By 1938, LaGuardia, a staunch supporter initially, began to publicly note something important.
What was that?
That the great strides being made in parks were not being matched in any other areas of public works, not even in areas like schools and hospitals in which the need was desperate.
So Moses's focus was too narrow, neglecting other vital needs.
That was LaGuardia's growing concern, and Moses frequently used a resignation ultimatum as a weapon to force his agenda.
Threatening to quit if he didn't get his way.
Repeatedly, demonstrating a significant failure in collaborative governance and a pattern of authoritarian control.
Any other examples of his controversial methods?
Another striking example of a systemic failure in public engagement and transparency was the arbitrary closure of Battery Park at the tip of Manhattan for 5 years.
5 years? Why?
With no stated reason given to the public. This was despite a concerted public fight to save Fort Clinton, a historical landmark located there. The public couldn't even see what was happening behind the high fences Moses had erected.
A deliberate breakdown in civic communication and accountability.
Exactly.
This truly shows us how failures aren't always about structural integrity or material properties. They can be profoundly systemic, political, social, and economic.
With long-lasting impacts on urban life, equity, and the fabric of society.
The human element, with its motivations, power dynamics, and biases, can be just as crucial a factor in failure as any technical specification.
It adds a whole new layer to our detective work.
Absolutely. And this idea isn't entirely new, is it? You mentioned ancient examples earlier.
Right. This understanding of systemic failure, or at least the importance of foundations and context, has roots in antiquity. Even architects like Palladio and Vitruvius were acutely aware of potential failures related to site selection and foundations.
Palladio, the Renaissance architect, and Vitruvius, the Roman.
Yes, they recognized these as absolutely critical to a building's longevity and stability. In the 4 books of architecture, Palladio offers very specific advice about foundations.
What'd he say?
He said pilings must be placed under all walls, not just the outside ones.
Why under the internal walls, too?
His reasoning was practical and direct. If the foundations of the middle walls are constructed differently from the outside ones, the inside walls could sink, while the piled outside ones remain unmoved.
Uneven settlement.
Exactly. This uneven settlement would not only be very disagreeable to the site, aesthetically displeasing, but would also cause all the walls to open and ruin the whole edifice.
So a subtle oversight in foundation design, a failure of holistic structural thinking.
Could lead to a complete structural breakdown.
It underscores the timeless importance of thoroughness and a holistic view right from the ground up, a lesson passed down for centuries.
And Vitruvius, writing even earlier in the 10 books on architecture, similarly emphasizes the critical nature of site selection.
Choosing the right place to build.
Yes. He describes rudimentary yet insightful forms of environmental assessment for building sites. For instance, he suggests examining the livers of animals that have grazed in an area to determine the healthiness of the site.
Examining animal livers? Seriously?
Yes, inferring environmental quality from biological indicators. A bit primitive by our standards, but the principle of site assessment was there.
What else did he advise?
More directly, he explicitly cautions against building in valleys enclosed between mountains.
Why not valleys?
Due to the presence of pestiferous vapors, probably stagnant air or marsh gases, and too great moisture, which he noted could not only corrupt stored goods, but also weaken the health of inhabitants.
So thinking about air quality and dampness even back then?
These ancient observations highlight a profound understanding that environmental factors and foundational stability have always been central to preventing building failures.
Lessons still enshrined in modern building codes, albeit with more sophisticated scientific methods.
Exactly. The core principles endure.
Okay, this brings us to a crucial question. How do we take all these hard-won lessons from historical and modern failures, from project deviations, material shortcomings, urban planning controversies, ancient foundational wisdom?
It's a lot of learning.
How do we transform them into something actionable that actively prevents future tragedies? How do we codify this invaluable, often painful knowledge?
Well, one of the most powerful and enduring mechanisms is the continuous development and rigorous enforcement of building codes.
Building codes, the rule books for construction?
Exactly. The Building Codes Illustrated source highlights this repeatedly, and every requirement is essentially a codified lesson. For example, fire partitions.
Walls designed to stop fire spread.
Yes. They are not just arbitrary walls. They are specifically required to separate dwelling units, like apartments, sleeping units, like hotel rooms, and corridors. This is a direct response to countless fires, where the rapid spread through unprotected spaces led to significant loss of life and property.
So the code reflects tragic experience.
Absolutely. Similarly, draft stopping is a requirement to restrict air movement in concealed combustible spaces, like attics or floor cavities.
Why is restricting air movement important?
It dramatically slows the propagation of fire and smoke. These aren't preventative measures born from theory, but from the stark reality of past fire failures.
So every time a new code is written or an old one is updated, it's often a direct result of a failure somewhere, a fire, an earthquake, a structural collapse.
Becoming a powerful testament to learning through adversity.
It's a continuous, often reactive, but ultimately essential cycle of improvement that literally saves lives and builds resilience into our infrastructure.
Absolutely. The code even specifies detailed requirements for seismic force-resisting systems, things designed to withstand earthquakes.
Like special types of framing.
Yes, including bearing wall systems, building frame systems, moment-resisting frames, and dual systems. Crucially, it dictates specific detailing for structural components to implement design requirements against seismic loads.
Can you give an example of that detailing?
Sure. Did you know that the requirement for ductile detailing in concrete frames, designing them to bend and absorb energy rather than snap rigidly, was a direct, hard-won lesson from major earthquakes in the 1970s and 80s?
What happened then?
Buildings with rigid, brittle connections collapsed catastrophically. Engineers realized true resilience meant allowing structures to fail safely, not just resist forces.
Fail safely? That sounds counterintuitive.
It means bending or yielding in a predictable way, absorbing energy without a sudden, total collapse, giving occupants time to escape. That's a profound insight. Sometimes failing safely is the ultimate design triumph, built on the back of past tragedies.
Wow. That is a different way to think about it.
Beyond structural integrity, the code addresses material performance. It classifies wall and ceiling finishes by their flame spread and smoke-developed indexes, Class A, B, C.
How quickly they burn and how much smoke they produce.
Exactly. This is based on rigorous testing protocols like NFPA 286, ASTM E84, or UL 723. It shows how specific material failures to resist fire or produce toxic smoke directly inform regulations.
So past fires influence what materials we can use inside buildings?
Directly. Furthermore, accessibility requirements often linked to the Americans with Disabilities Act, ADA, and the Federal Fair Housing Act, FFHA.
Things like ramps, wider doors, accessible restrooms.
Yes.
Yeah.
These reflect a societal learning curve about past failures in equitable design and universal access to the built environment, ensuring everyone can use a building safely and comfortably.
When you walk into any modern building, every fire exit sign, every sprinkler head, every accessible ramp, and even the way materials are chosen, these are all physical manifestations of lessons learned from past failures.
And the immense collective responsibility of preventing future ones.
It's a silent guardian, a layer of protection meticulously built into our environment, continuously evolving.
And this learning isn't just in codes. Our sources on project management similarly show a clear evolution towards anticipating and managing failures proactively.
Embedding resilience into the methodology itself.
Yes, the PMBO guide emphasizes that adapting should be done with a holistic view, employing a proper change of control process to prevent issues like the scope creep we mentioned earlier.
Building flexibility in, but in a controlled way.
Exactly. Ensuring that adjustments don't accidentally create new problems or balloon the project unnecessarily.
That's fascinating. So it's not just about reacting to a crisis once it erupts.
No, it's about building resilience and adaptability into the very fabric of how projects are managed from the outset.
Designing a system that can absorb shocks, adjust its course gracefully, and prevent those small deviations from spiraling into larger failures.
Precisely. And the critical path method in scheduling, discussed in both Construction Management and Construction Management Jumpstart, is a prime example of this proactive approach.
The critical path, how does that work?
This method helps project managers identify a sequence of activities, the critical path, where any delay in a single task will directly delay the entire project.
So these are the tasks with no wiggle room.
Exactly. These tasks have no float, meaning zero tolerance for schedule slippage. By identifying this critical path, project managers gain a direct mechanism to focus resources, closely monitor progress,
And prevent schedule failures before they happen.
allowing for timely and targeted intervention on high-priority items. It's about managing risk proactively.
That's incredibly insightful. And this kind of thinking extends beyond just construction, doesn't it?
Oh, absolutely.
Even identifying bottlenecks and understanding key metrics like throughput, inventory, and operational expense, as discussed in Eliyahu Goldratt's seminal work, The Goal.
A classic book on process improvement.
That's a profound form of failure analysis for business processes too, isn't it?
It absolutely is. It's about recognizing the constraints within any system, be it a manufacturing plant or a service organization, that limit its overall performance.
The parts that cause it to fail to meet its full potential.
Precisely. The goal emphasizes focusing on these core problems rather than the symptoms to achieve significant lasting results.
Don't just treat the symptom, find the root cause.
Exactly. This principle, profoundly applicable not only to manufacturing but also to service organizations and project management, directly guides how organizations learn from process failures.
It shifts the focus beyond blaming individuals for specific mistakes.
To understanding the system's inherent behavior and structure that allows those problems to occur, it's a holistic approach derived from a deep understanding of what causes a system to underperform.
These management techniques, from critical path analysis to bottleneck theory, are designed to anticipate and mitigate those smaller failures.
The ones that, if left unaddressed, can snowball into major disruptions.
Keeping projects on track and on budget. They truly embody the idea of continuous improvement born from an ongoing analysis of potential and actual deviations.
It's learning embedded in the process.
This entire discussion about failure analysis seems to mark a crucial shift in mindset, moving away from a punitive search for blame,
which is often the first instinct,
and towards a deeper understanding of the interconnectedness of events, acknowledging that problems rarely have a single, simple cause.
That's a truly crucial insight, and it's powerfully articulated in Dinello Meadows' Thinking in Systems.
A foundational text on systems thinking.
Yes. She states very pointedly, you'll stop looking for who's to blame. Instead, you'll start asking, what's the system?
What's the system? That changes everything.
This perspective is transformative. The concept of feedback loops is central here, revealing how a system can cause its own behavior.
The system itself creates the outcome.
Often, yes. A failure isn't just an isolated incident. It's frequently an emergent property of how different parts of the system interact over time, amplifying or dampening certain tendencies.
So a failure might not be attributable to a single error or a single individual, but rather an emergent property of how different parts of a complex system interact and influence each other over time.
That's a truly powerful idea. It fundamentally shifts our perspective from individual accountability to systemic understanding.
Encouraging us to look at the whole picture, the dynamics, the patterns, rather than just the immediate visible breakdown.
Exactly. This systems thinking also explains why delays within a balancing feedback loop can cause the system to oscillate, leading to unexpected and often undesirable behavior.
Oscillate, like swinging back and forth.
Yes. Think back to our discussion of Robert Moses. His singular focus on parkways, amplified by his resignation ultimatum weapon, created a powerful growth feedback loop for park construction.
Okay.
Mayor LaGuardia's growing awareness of desperate needs in schools and hospitals was a critical balancing signal, trying to pull resources elsewhere.
But Moses resisted.
Yes. His command and control approach meant the system overcorrected on park development, with significant delays in responding to other community needs. This resulted in a societal oscillation,
Swinging too far in one direction before the community could effectively push back.
leading to long-term failures in equitable urban development that we still grapple with today. It also highlights limits to growth archetypes.
Limits to growth.
These show that any physical growing system, whether a population, a corporation, or a products market, will inevitably run into some kind of constraint sooner or later.
Nothing grows forever.
Right. Understanding these inherent limits and feedback mechanisms is key to truly analyzing and learning from systemic failures, preventing the same patterns from repeating.
This systems perspective helps us understand that when something fails, it's rarely a simple cause and effect.
It's almost always more complex.
It's often a complex interplay of forces, dynamic relationships, and feedback loops. And truly understanding that deep complexity is the essential first step to genuine learning.
Helping us avoid superficial fixes and address the deeper underlying dynamics that drive a system's behavior. Hashtag the immense responsibility and continuous improvement.
Okay, this ongoing discussion of failure, prevention, and learning inevitably brings up the profound idea of responsibility.
The crucial aspect.
What do our sources tell us about the layers of accountability that come with designing and constructing our built world?
Well, the Construction Management Jumpstart emphasizes risk identification and mitigation and value generation as paramount.
Finding risks early and adding value.
Yes, particularly through the early involvement of contractors and architects in the pre-construction phase. This upfront analysis is clearly stated as beneficial to both the owner and the project overall.
So this means that the responsibility for preventing future failures is baked into the project from the very beginning.
Long before ground is even broken, it's a proactive rather than reactive stance, making foresight a shared accountability across the team.
So preventing future failures isn't just about fixing things once they break. It's an inherent part of the initial planning.
It makes the entire project team collectively responsible for foresight and proactive problem solving, rather than merely reactive damage control once a problem emerges.
What about when things do go wrong unexpectedly during construction?
Project management in construction delves into the intricacies for things like geotechnical reports and disclaimers.
Reports about soil conditions.
Exactly. It notes that an allowance or contingency sum set aside for unforeseen ground conditions is for the owner's benefit, not the contractor's.
Meaning the contractor can't just automatically claim that money.
Right. This highlights the contractor's specific responsibility to thoroughly document their claim of encountering conditions that differ materially from those anticipated, if they are to seek additional compensation or time.
They have to prove the conditions were truly unexpected and different.
Yes. This isn't just contractual boilerplate. It underscores a profound contractual and ethical imperative. Designers and builders carry an immense responsibility to be transparent and accountable when unforeseen challenges arise.
Challenges that could lead to project failures.
Protecting all parties involved and ensuring that risks are appropriately managed and costed.
That's a critical point. The legal and contractual frameworks around construction embody the immense responsibility designers and builders carry.
It's about delivering what's promised, managing unforeseen risks.
And ultimately ensuring human safety and safeguarding massive financial investments. It's a field where the stakes are incredibly high.
Absolutely. And the scope of this responsibility extends far beyond the immediate project now.
How so?
It now encompasses global concerns, particularly in the critical drive for sustainability. The Construction Management Jumpstart references the landmark Brundtland Report.
From the UN back in the 80s.
Yes, which offers a foundational definition. Sustainable means meeting the needs of the present without compromising the ability of future generations to meet their own needs.
That shifts the scope of what constitutes a failure dramatically, doesn't it?
It really does. It broadens failure to include not just current project shortcomings, but also the long-term intergenerational impact on environmental resources and societal well-being.
That's a truly profound shift in responsibility from simply building something well for today.
To ensuring it doesn't fail future generations by depleting essential resources, exacerbating climate change, or causing irreparable environmental harm.
It's a truly holistic and long-term view of what constitutes project success and, conversely, what defines its ultimate failure.
And sustainable construction discusses how green building requirements are actively being incorporated into mainstream building codes.
Making sustainability part of the standard rules.
Yes, citing specific examples like ASHRE 189.1/2014 to drive sustainable design into everyday practices. This reflects a collective learning process, a societal realization about the failure of traditional construction to adequately address environmental impact and resource consumption.
Learning from our past environmental impacts.
Exactly. The source introduces sophisticated concepts like ecological footprint.
Measuring the land area needed to support a building.
Right, over its life cycle. And ecological rucksack, which quantifies the total mass of materials processed and energy consumed to produce a unit mass of a specific material, like steel or concrete.
So, measuring the hidden environmental cost of materials.
Precisely. These aren't just academic terms. They are powerful analytical tools used to articulate performance goals for green buildings.
Highlighting the broader environmental and ethical implications of our material choices and construction methods, guiding us away from future ecological failures.
That's the aim.
Our collective ability to prevent these immense environmental failures in the built world rests on this evolving understanding and commitment to responsible design and construction.
It's a testament to how the very definition of failure itself expands as our knowledge grows, our ethical frameworks mature, and our understanding of interconnected systems deepens.
Ultimately, this entire deep dive, this meticulous examination of what goes wrong, it feels like it's fundamentally driven by a core human impulse. The drive to understand, right? To get to the bottom of things, to peel back the layers until the truth is revealed, and ultimately to master our environment.
This is precisely where the wisdom from Matthew Crawford's shop class as Soulcraft truly resonates.
A great book about the value of manual work and understanding how things work.
Yes. He describes a compulsion to get to the bottom of things, to gape them open and clean them out, an almost primal desire, which he even calls a forensic pretense.
A forensic pretense, like pretending to be a detective even with everyday objects.
Kind of. This inherent drive for thoroughness, for deep, unfiltered understanding, is absolutely essential for true failure analysis. It's about not letting a problem go unsolved.
A deep-seated curiosity that pushes us to investigate, to disassemble, and to reveal the hidden mechanics behind a malfunction.
It's the craftsperson's desire for perfection, born from intimate engagement with the material world.
That's a beautiful way to put it. So the very act of failure analysis isn't just a technical exercise, it stems from a profound human curiosity and a desire for mastery.
Much like an artisan mastering their craft through dedicated practice, meticulous attention to detail.
And critically, learning from every mistake, every broken piece, every flawed attempt.
That's how true expertise is forged.
Absolutely.
Exactly. And Marc-Antoine Logier's lectures on architecture from the 18th century offers a timeless reminder.
What did Logier say?
He said, "Architecture is an art derived from reason only." But then he provides a stark, practical analogy.
Okay.
In a case of peril, we ought to make a point of blending our energies towards that part where the danger is. When the house is on fire, we do not discuss the question whether it's built according to the rules of Vignola or after the pattern of Gothic habitations. We run for water.
Right. Act first based on reason. Don't debate theory in an emergency.
Precisely. The emphasis here is unequivocally on reasoning, on empirical analysis, true science, to assess and retrieve a situation, and crucially, to learn from it.
It isn't about rigid adherence to dogma or tradition.
But about applying intelligence and hard-won experience to real-world problems. This mindset of tireless investigation, driven by reason and a commitment to mastery.
That's what transforms every failure into a profound opportunity to make the world a safer, more efficient, and more knowledgeable place for everyone.
Well said. That's the ultimate value. Hashtag outro.
From understanding why a project veers off course, to meticulously dissecting the inherent properties of materials, to analyzing the vast complexities and human dimensions of urban planning.
This has been quite a journey.
Our deep dive into failure analysis has shown us that every misstep, every breakdown, every deviation from the ideal holds an invaluable lesson.
There's always something to learn.
It's a powerful testament to human ingenuity that we don't just endure failures, but we interrogate them, we learn from them, and we ultimately build a more resilient and wiser future because of them.
And if we truly connect this to the bigger picture, consider this. How many of the unforeseen factors or breakdowns we discussed today actually reveal the deeper, often hidden system at play?
A system we might not have fully understood until it fractured.
Exactly.
Yeah.
What if truly understanding failure isn't just about fixing a specific problem, but about fundamentally reevaluating our core assumptions?
Assumptions not just about the structure, but about the very systems, values, and responsibilities embedded in how we design, build, and interact with our world.
And maybe think about this. What current best practices or widely accepted norms might one day be seen as glaring failures by future generations?
Prompting their own profound lessons and challenging our present-day wisdom.
Something to ponder.